Okay, I can show you how to calculate the displacement imposed due to the distribute load on an elastic half space. That is the problem, typical problem of a shallow foundation. We can start by considering this exercise that you can find in BIP. And here you can find the property of the elastic space and the value of the foundation and of the load. And I'm going to consider two different cases, flexible and rigid foundation. Okay, you can open Sap2000 because you can find the evaluation version on the website of SAP. I can start with the new model. Pay attention on the unity, of course. In geotechnical case, we can use kilonewton and meter to have kilopascal and this kind of unities. Okay, we can select grid and create initial grid. Is not important because I'm going to modify this grid by considering our dimension. We have 10 by 10 by 10 soil with discretization of a finite element having 0.5 meter of dimension. So I'm going to create this kind of situation, 0.51. Here, pay attention, you can add directly and the SAP will add directly with the constant step of 0.5. I can go till 10 and also here. And also here. Here you can decide if you want to view or hide the grid lines. Okay, we have created our grid because it's important, because in SAP only if you have the grid you can select the points. If you don't have the grid you cannot select and connect the point. Okay, now we can create a material, new material. We don't have a space for soil, but we can create other material, and we can assign the properties. We can put here 18 and the elastic modulus is this one and the Poisson ratio is this 0.33. This is not important for now. And okay, if you want to see nonlinear behavior, you have to switch to advanced properties. Here you have the type of plastic properties, and here you can select also the nonlinear behavior. By you can see here the friction angle, the hysteresis type, and the stress strain data. You can also select this kind of parameter. We can remove these materials. Okay. Now we have to design the three-dimensional mesh starting from a shell mesh. You can see in the bottom your different position along the zeta direction. If you are in the xy plane. Okay, we can create a rectangular area and perform an extrusion of this area. I'm going to extrude only, of course, in positive direction of 10 meter in one time. So only one time of element, 10 meter of extrusion. And solid 1 will be the name of the solid, the assigned property of the solid. You can see I do again because something I'm not sure to have okay. This is our three-dimensional mesh. We can look at the property in define section properties. We can look at the properties of our solid if it takes the right material. I use a solid 1 if you remember. You can see solid 1 is not the right material. I want to use matte. Okay, I'm going to define a material. I'm going to call it soil to have a better identification. Okay. So I can check again in solid properties if solid 1, that is this one, is the one related to the soil. Okay. I can also create a second material for the foundation, maybe concrete. I can call it concrete. I'm going to use 25 and the modulus and the Poisson ratio of the concrete for now. And you can select the second solid properties and assign concrete. And I'm going to call it foundation. Okay, now we have to divide the mesh because now is one big singular element. So divide the mesh in edit, divide solids. We want the step of 0.5, so 20 different elements in each direction. Okay, now I have created my mesh and I can not delete, but I can hide the grid. Okay, now we have the mesh. We can start with the, and we have to assign lateral boundary condition on each faces of our soil. Again, we can assign encaster for this first example. So fixed condition on each node. Pay always attention on the right direction. Now we are in the zeta x direction and y is equal to 0. Don't go inside the soil to apply the restraint. Pay attention on this particular. We can move in the y direction by this move down or move up. You can see that it's changing. Now we are in 10 meters, so in the opposite side. And okay, is the one in which we are interested. And we can do the same thing, again restraint. We can do the same thing also in the y zeta plane, paying attention in the x value. 10. Okay, selecting the node. Okay, now we have restrained all the soil, and the restraint are all around and everything is fixed. It is interesting to try to apply, for example, a pinless support that permits the vertical displacement but not the horizontal one, to understand the differences. Okay, now the soil is ready, we can draw the foundation. I'm going to the top of my soil, so XY plane and zeta direction, and I'm going to design the foundation. Starting from an area, I'm going to extrude an area. So first of all, I have to draw the area, rectangular area. We can start with section 1, is then I'm going to extrude it. So from the middle, 5, 5. The dimension of my base is 3 by 3. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. One, two, three, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, this is my, now it's difficult to see because everything is red, but I can select it. This is my 3 per 3 meters foundation. I'm going to extrude it. Again, edit, areas, extrude to solid, delete source object, and we can put a dimension of 1 meter, for example. And I'm going to select solid 2, foundation or solid 2. Okay, if we want to see different color, we can select view colors by sections. And you will see that the soil is green and the foundation is blue. We can see in the 3D view, this is our foundation, this is our soil. Maybe 1 meter is very high, but okay, for this exercise, you can calibrate it. Okay, if you want to look inside, we can go in 3.5 to 6.5 in the y direction or in the x direction, and you can see the section with the soil and the foundation. Okay, now we have the foundation and we have the soil. We have to divide the foundation into different elements, because if you do not divide the foundation, you will not have the communication between the elements of the foundation, the elements of the soil. So I'm going to divide this foundation with the same mesh of the soil. So I need 6 by 6 division, and in the zeta direction I can divide by 2 different elements. Okay, now all the mesh is in communication because all the nodes are superimposed. I have 2 division in zeta and 1 6 division in the x and y direction. We can see also a different view. maybe it's better to understand soil and foundation. Now we can go and apply the loads. We can start with a very flexible foundation by modifying the material, the concrete. Now is something that is 1, 2, 3, 4, 5, 6. We can remove to 0, for example. We can create, first of all, an elastic modulus, and we're going to remove to 0 to have a very flexible value, a very low value of the elastic modulus. And I'm going to apply now the load. First of all, you have to create a load patterns. Here is really important because with 1 here, you will consider the self-weight inside the load pattern, the self-weight of the soil and of the foundation. Now we are interested only in the increments, so now is not important the self-weight. We are not interested in the geostatical stresses, but only in the increment of stresses due to loads. Okay, we can modify the load pattern and create the load case that will be a linear static, really simple linear static load case. Here you have a lot of options, static, modal, response spectrum, time history, buckling for a very refined analysis. Now we are only interested in linear static analysis because we don't have nonlinearity, we are in the elastic half space, so everything in linear static. Pay attention to the scale factor, that is the factor that will be multiply your loads. Okay. We can assign the loads to the solid. First of all, I'm going to define a grid because in the zeta we don't have all the grid for the soil. Okay, the top is 11. Okay, I'm going to the top of the soil, of the foundation, sorry. 11. I'm going to select these elements and to apply the load. Phase 6, pay attention on the phase, and phase 6, the load in the phase 6 is in the zeta direction in the gravity, so is okay for us, and we have to apply 44.2. Okay, now we have the load, we have the foundation, we can run the analysis. You have always to assign a name to your model. The analysis will be really fast because we don't have nonlinearity, so it's a really simple analysis. You can see also the menu with all the information about the analysis and the iteration if it's a nonlinear analysis. Okay, now we can see the displacement, show the formed shape, a case 1, I didn't rename it the load case, but a case 1 is our load case. You can see the displacement here is higher in the middle. We can go in a section, okay. We have a displacement equal to 1.6 but in the middle is, you can look in the exact middle here. (1.82). This case is not a real case with rigid or flexible foundation, because we have to calibrate the rigidity of the foundation with respect to the rigidity of the soil. So we can create a really stiff material for the concrete to be sure that is really rigid foundation, a really rigid foundation, to understand how the stresses and the displacement change. You can see that this is completely rigid because all the points have the same displacement, exactly the same. You can go to see also the pressure or the stresses, if you prefer to see the stresses in the zeta direction. These are our stresses. You can move, of course, in all the direction. But now if we want to create, to be sure, to create a really flexible foundation, the most simplest thing to do is to remove this foundation and apply directly the load on the soil. You can select by properties directly the foundation only. Okay, to delete I press Ctrl in the keyboards. Okay, now I'm going to the top and I'm going to apply directly the load on the soil. Okay, again assign load, pressure, the same pressure that I applied previously, and run again the analysis. Okay, we can go to see the displacement in the x zeta plan. Okay, now you can see that these displacements are greater, that are 2.3. So the case, the very first case was not a really flexible foundation, because as you can see, the perfect displacement for the flexible foundation is 2.39. So when you insert an element over your soil, you have to be sure that the ratio between the rigidity of your foundation and your soil bring you to a creation of a rigid or a flexible foundation. Is always a relative situation. Depends on your foundation and on your soil. But if you want to be sure that you want to study the flexible foundation, you can apply directly the load on the soil. So for this problem, the finite element solution is 2.3. You can check with the theoretical and with the theoretical equations. We can see also the distribution, stresses distribution. That is a really interesting case because you can see that the previous one are completely different. And this is the classical solution of Boussinesq, and you can check it by the theoretical formula, by checking in the middle of the soil and in the other parts. You can also try to modify these boundary conditions to see if there are some differences in the displacement or not. Thank you for your attention, and if you have any question, please.